Hey everybody. Today we're tackling one of the most famous, or maybe infamous problems in all of probability, the birthday problem. It goes like this. How many people have to arrive at a party in order for there to be a 50% chance that two of them at least share the same birthday? Assume there are 365 days in a year, which isn't quite true, and that all birthdays are equally likely, and that's definitely not true. One simple approach considers ordered sets of size n, each element of which can have 365 different values. So what I'm talking about here is if you have n people, the first one arriving can have 365 different birthdays, the second one can have 365 different birthdays, and so on. All of those counts are independent of one another, so the sample space in the birthday problem has size 365 to the n. Next, we need to count the number of ways that a set like that can have no repeated elements. Imagining these people arriving one at a time, for one individual there are 365 possible birthdays with no repeated birthdays. When the second one gets there, there's 364 different birthdays that that person could have without there being a repeat. Then 363 for the second, and so on. So the number of sets of size n with no repeats is 365 times 364, and we keep multiplying until we have n terms. Saying that slightly more briefly, a bit more mathematically, the number of sets of size n with no repeats is 365 per mut n. To compute the probability of having at least one repeated birthday, we'll do 1 minus the probability that there is no repeated birthday. And that probability is going to be the number of ways we can have no repeats divided by the total number of possibilities. With a little bit of algebraic simplification, just sort of neatening things up, we get 1 minus 365 over 365 times 364 over 365, etc., until that product has n terms. From here, we want to tackle it numerically. I used R, and I plugged in the values n equals 1 through n equals 50, and I made this visualization, along with a cutoff value of p equals 0.50. We want to get the first bar here that actually is taller than that dotted line. The result ends up being n equals 23, where the probability of a repeated birthday is about 50.7%. I think for most people that n is smaller than you might expect. By the way, when n is 50, there's already over a 97% chance of at least one repeated birthday. So the probability of at least one repeat gets big pretty fast.